Here's a definition of a regular Sturm-Liouville problem again, right? So it has a differential equation, it has two boundary conditions, and then we are looking for the lambda and we are looking for the phi, which we call the eigenpair, phi and lambda. There are quite some interesting properties of these Sturm-Liouville problems, which I just summarized in this video. There are mathematical proofs in the textbook, but I will not go through the proofs because we are not going to test you on the proofs. But you should understand what's going on. Let's start here with theorem 4.2. So the spectrum, well, these were all the eigenvalues lambda n. So the spectrum of a regular Sturm-Liouville problem is a countable infinite set with no limit points. That is an infinite discrete set. What does this mean? Well, okay, let's draw a little tiny picture here. The spectral values, the lambda n's, in general, they can be complex values. So I'm plotting the complex plane. Okay, so then here is the real axis, and here is the imaginary axis. We will find later that the eigenvalues are actually all real, so they're all sitting on the real axis. And then what does it say? There are discrete points, so they're just points on the axis. And then infinite discrete set, so they will actually go to infinity along this axis. That's it. And having no limit points means they don't get arbitrarily close. They keep their distance. So these are the lambda n. And the corresponding eigenfunctions, like here in theorem 4.3, they are orthogonal relative to a weighted integral, so that the inner product of two functions f and g is defined as integral fg sigma dx. Well, the sigma was one of the functions of the Sturm-Liouville problem. And so this shows up here at the weight in the integral. And so now this integral has to be equal to 0. Coming back to the previous example with the sine functions, for example, we know that the integral from 0 to L of sine n pi x divided by L and sine m pi x divided by L dx is equal to 0 for different n and m. So that's the same condition. So then f would be sine n pi x over L, g would be sine m pi x over L, and they're orthogonal in the integral, and here the weight function sigma would be equal to 1. Theorem 4.4. If lambda is an eigenvalue, then lambda is real. This is something I mentioned already. And then if you have two eigenfunctions corresponding to lambda, then they are linear dependent. So then you can write one as a linear multiple of the other. Okay, so again, this is the same picture as before. The eigenvalues are all discrete sets on the real axis if this is the complex plane.